We are finally at the end of our journey into deciding the LTL model checking problem. This is the procedure that we have described and have proved to be correct. Starting with an LTS M, a state S0 and a formula phi. In step 1, we compute the automaton ought associated to the negation of phi. In step 2, we take the product between M S0 and ought, obtaining another automaton, say ought prime. In step 3, we check if the language of ought prime is empty. If it is empty, then we conclude that M in S0 satisfies phi. If it is not empty, then we conclude that M in S0 does not satisfy phi. Let us complete our running example to show a fully worked out version of the model checking algorithm. We take the formula phi to be not eventually A. Then not phi can be identified with eventually A. Remember that the bar denotes negation, the same thing as the not symbol, and we identify not phi with phi itself. Let M be the LTS shown here. We consider the question of whether M in state S0 satisfies phi, which is an instance of the model checking problem. We apply step 1 to build the automaton ought of not phi, where not phi is eventually A. We have already done this as part of our running example, and this is the resulted automaton shown on the right. In step 2, we build a product automaton between the transition system and with its chosen state and the automaton. Again, we have already done this as part of our running examples, and the resulted product automaton is shown here. Let's clean it up a bit by calling its states Q1, Q2, and Q3. The exact content of its states, namely the LTS states and the various scenarios, were useful when constructing the automaton, but will not be needed for deciding satisfaction. So writing Q1, Q2, and Q3 for them should do. On the other hand, the LTS state will be needed for producing counterexamples that I will discuss later. But for now, let's forget about them. In step 3, we check the non-emptiness of the language accepted by this product automaton by looking at its underlying graph shown on the right. We compute its maximal non-trivial strongly connected components. There are two of them. One is Q1, Q2, and the other one is Q3. Q1, Q2 is accessible from an initial state of the automaton. Here, the only initial state, Q2. And intersects all the accepting sets of the automaton. Here, the only accepting set, Q1, Q3, in that they have Q1 in common. So the accepted language of the automaton is non-empty, which allows us to conclude that M in state S0 satisfies phi. Let's see for ourselves that our conclusion is correct. The conclusion obtained by the general purpose algorithm that I showed on the previous slide is correct. Remember that phi is not eventually A, and it is indeed not the case that M in S0 satisfies phi. Because there is a path starting in S0. For example, S0, S1 to the infinity. So S0, S1 repeated infinitely. And this path satisfies eventually A, hence does not satisfy phi, which is not eventually A. A parenthesis here. Incidentally, our LTS in S0 does not satisfy eventually A either, because there is a path, namely the one looping in S0, on which A does not hold. So it turns out that this LTS in S0 satisfies neither eventually A nor not eventually A. End of parenthesis. Now a question we may ask: if the answer is no, meaning the LTS in the given state does not satisfy the formula, as was the case here, can the model checking algorithm be amended to produce a counterexample path? And the answer is yes, with a bit of additional tracking. Here is the context, the relevant context for our example, which produced the no answer to the given instance of the model checking problem. I show here the essential pieces only: the underlying graph of the product automaton, its set of initial states, here just the state Q2, and its set of accepting states, accepting sets, here just the set of states Q1, Q3. The conclusion that the accepted language was non-empty, hence that satisfaction does not hold, was drawn after exhibiting a maximal non-trivial strongly connected component, namely Q1, Q2, which is accessible from the initial state and intersects the only accepting set. Remember from the previous lemma that from the strongly connected component, we can produce an accepting lasso. It essentially contains information about an accepting lasso. The lasso starts with a path from the initial state to our strongly connected component. Here, just the singleton path Q2, and continues with a cycle that covers our entire strongly connected component. So the lasso is Q2, Q1, Q2. In this example, our lasso here is merely a cycle, but in general, we could have proper lassos. If, in order to access the strongly connected component, we would need a path of length longer than 0. Now, it is time to remember that the states of our product automaton, it's time to remember how these states look like. So remember that Q1, Q2, and Q3 denote some specific product states, which are now shown in the picture. Our desired counterexample path is obtained by taking the LTS state component of the product states of our accepting lasso. Here, we get S0, S1, so from Q2, Q1, Q2, we get their components S0, S1, S0. These are the states in the LTS. And then we repeat infinitely the cycle part of the lasso. Here, we obtain the paths S0, S1 infinitely. And indeed, this path is our counterexample for phi. In summary, if the answer to an instance of the model checking problem is negative, we can produce a counterexample, which is a path in the LTS that does not satisfy our formula. This is really the reason for which the formula is not true. This counterexample is obtained by taking the LTS state component of the product states of an accepting lasso that witnesses non-emptiness of the product automaton's language. I've described the procedure for building a counterexample on a particular instance, but as you can see, the procedure applies in general for any instance of the model checking problem.